In this lecture, we'd like to look at the MSP430 general purpose input-output ports. Recommended reading is on Wikipedia. Look up tri-state logic or three-state logic. Also, you can see some links on the class wiki, which are quite useful. And my thanks to Mark Clement and BYU for most of the material in these slides. Our learning objectives is, after we've been discussing the microarchitecture and studying the assignments here, you should be able to understand GPIO ports and use them. So the topics to cover are memory mapped input-output and I/O ports. So what is memory mapped input-output? Well, I should first notice before we get into this that these slides were prepared for the MSP430 G2553, and we have the MSP430 F5529. And so this is what I'm going to describe here is slightly simpler than what we have because our processor is actually more powerful than the one that this was, the processor that these slides were prepared for. And so you need to actually look at the MSP430 F5529.cmd file to see some of the differences there. It's in the includes directory, by the way. So in the G series processor, there's a 16-bit address bus. Actually, on our processor, we have a 20-bit address bus, but we're looking at the simple situation now. In the 16-bit address bus, they reserve the lower 200 hex registers, or 512 registers, or memory locations for peripherals. That means input-output devices. So when you look at those 16 bits, basically some of those address bits will send you off to the I/O. And so basically it's kind of like this. When you look at bits 9 through 15, that goes into a NOR gate, if it's any of those. And if it's not those, then it's basically checking to see whether you're on those, those lower those, I guess it's the higher peripherals there, the ones, the 512 bytes that are where the I/O is. So it's high if and only if bits 9 through 15 are low. That means we're in the in the last 200 bytes. And then we take that the address, part of the address, 0 through 8, 9 bits, and we run that to a decoder. It takes 9 bits and it decodes 512 things, and that allows us to get 512 peripherals there, and it will select which one is in use based on what we actually sent to the memory bus, and the address bus, and so this whole circuit you're seeing here is known as an address bus decoder, and we're basically looking for these peripherals here. In which case, when we get the peripherals, they're enabled with those 512 signals. So you can see in this case there are not all zeros, so you wouldn't get anything, but in this case you would. So that device would be selected there. So we look at the G series thing here. Remember, our processor is more complicated. It has more I/O options, and you can look at those I/O options in and the MSP430/include, and then the MSP430 F5529.command file for more details and the exact addresses. And you can also look at the user's guide for the MSP430 X5XX and X6XX processors, and it will tell you in there more about how to use these devices. And you can look at the data sheet to find out exactly which peripherals are actually available, because they have different chips with different peripheral configurations. So if you look up on top, we have the high memory. That's flash memory. From in the G series, it's from F800 hex up to all the way up to the top FFFF. That's flash memory. And then the lower 0 through 01FF, those 200 hex things are peripherals and special function registers. And then there's RAM between 200 and 400. That's the random access memory that you can store variables in that are changing. So memory mapped I/O is where your input-output ports are just in with all the rest of your memory. The ports connect the CPU to the outside world, the I/O ports. The ports are 8-bit memory locations, and their general purpose I/O ports can be read or written. In other words, they could be input or output. Each bit is independently programmable. This isn't always the case. Some simpler processes you have to program the whole port one way or the other, but in these processors you can have some pins be inputs and some be outputs. And you can also get edge select input interrupt capability. In other words, you can get an interrupt in the processor when something changes on one of these ports, which is actually very handy. So if we look closely at some of these peripheral memories down at memory 20, 21, and 22, 22 in this G series processor is the data direction register, which determines whether the P1 is input or output. And there are two other memory locations, one of them that you write to for output, and then the other one you read from for when you have it set up as input. So here's some assembly language instructions that would write to the port 1 direct. Well, first of all, it sets the data direction to be output for those bits that are set in 0x41, and then it actually takes and makes one of those bits high with bis.b, the 0th bit. So that memory came right out of the peripheral section there. We just kind of blew it up. And then if you want to, you could XOR it, so that would toggle the thing every time, which is handy. So let's look at how a digital I/O port works. So there's this thing called the data direction register, and you might have a number of ports. In general, the TI documentation puts an X in for those things. So if you look at PXDIR, that X could be a 0, 1, 2, 3, 4, how many ports you've got, and it depends on which processor you're using. And the data direction register basically tells the processor whether this port is input or output. And the default is input, and that's 0. If the data direction register has 0 in a certain bit position, then that bit on the port is an input. If it has a 1, then the port is an output. So the first thing you have to do is set the data direction register. And then if you're reading it, you can read the input, port whatever in. And of course, the bit is a 0 if the input port is low, and a 1 if the input port is high. And then if you want to use the port as an output, maybe it's connected to an LED, you can actually write a 1 to a port pin, and that will make the LED turn on, or put a 0 and it'll make it turn off, assuming the LED is hooked to ground with probably a current limiting resistor. If it's hooked to VCC, then it would be the opposite of that. So note that the output register can also be read from, just in case you forgot what you put there and you want to modify it and change things. So the output register can be read from as well. So here's some practical notes. Ports are 8 bits. Remember that. Use the .b instructions when accessing them. Do not use the .w instructions because that will actually change more than what you want. It will change the next memory location up, which could do some things that you were not expecting. Inputs can be floating. In other words, they can be pulled up or pulled down. They are controlled with PXREN and PX out. PXREN is another register that's the resistor enable register, and you can make them pulled up or pulled down with that PXREN and PX out. You need to look at the data or the user's guide to understand all that exactly, and you probably don't understand pull-up resistors very well yet, but hopefully we'll go over that here after a while. That's kind of a circuits thing. Other functions can be connected to the I/O pins, and so some chips have more than just GPIO on some ports. Like there might be a timer or some other things, and you'd use the PX or whatever the SEL register, the P whatever SEL register, to select those other special peripherals that are more complicated than general purpose input output. So if you look for us in the chapter 12 of SLAU 2080.pdf, that's the MSP430 X50 529 user guide, and it also includes a bunch of other processors as well in that series. But that chapter tells you all about connecting peripherals and so on, and GPIO. Oops. So that's basically the end of the lecture on GPIO.